Many mysteries of physics remain unsolved to this day, even though numerous brilliant minds are working intensively on them. They are the leading authorities in the natural sciences, producing pioneers such as Galileo Galilei with his groundbreaking experiments and Isaac Newton with the founding of classical physics, which was brought into the modern era by Albert Einstein. Physics, once considered the church of the third millennium, no longer needs dogmatic beliefs and no longer hides its ignorance behind elegant theories. Instead, physicists have advanced far into the highest spheres of knowledge with their findings. The last great questions, such as the origin of the universe and its possible end, have been addressed. And yet, a significant portion of the cosmos remains hidden from so-called exact science. This is a scandal, not because the limits of human horizons have been reached, but on the contrary, because never before have humans penetrated so far into the limits of the universe with their instruments and measuring devices. While the naked eye can see around 6,000 stars in the sky, today, thanks to modern telescopes, astronomers are able to detect around 50 billion galaxies, each with systems of billions of stars. Astronomers have a precise understanding of how galaxies structure themselves, which is a direct reflection of the forces that existed at the beginning of the cosmos. However, a particular mystery is revealed in our own cosmic environment, the Milky Way, which astronomers know better than any other. With a diameter of around 120,000 light-years and a number of stars of around 300 billion, physicists can, thanks to their galactic sensors, specify exactly how much mass is present in our Milky Way. Based on the law of gravity, they can deduce how fast the stars revolve around the galactic center, which they can then measure with their highly sensitive equipment. The result has been shocking for 85 years. The observed mass would have to be 400 times larger than what is actually observed. Since then, physicists have been talking about dark matter because it is still unknown what and where this mass is located. Their existence is essential for the laws of physics to remain valid. It remains an unsolved mystery of physics. About a quarter of the world, 23% to be precise, is made up of dark matter, but the situation is getting worse. The Hubble Space Telescope was able to see further into the cosmos than ever before. His camera stayed open for 4 months. Astronomers discovered that the universe is expanding faster and faster. This can only be explained if there is an energy that counteracts gravity on a large scale, even though it should normally pull everything together. Physicists have been calling this dark energy for 25 years because it is still unclear what exactly this energy is and where it comes from. If the laws of physics are correct, our world consists of 72% dark energy. Without this dark energy, the astronomers' observations cannot be explained. In summary, 95% of the universe consists of matter that is different from what terrestrial researchers can study in their laboratories. Despite the use of sophisticated telescopes and sophisticated methods, we only know a fraction of 5% of the universe. We inhabit a galaxy made up of millions of stars, and is gigantic in size, approximately 120,000 light-years across. Our Sun is located in one of the branches of this galaxy. However, this galaxy is not static, but rotates like a giant carousel, with one revolution taking about 230 million years. This corresponds to our current worldview. looking back, it becomes clear that our worldview is constantly changing. Proof of this is the Foucault pendulum, which detects the rotation of the Earth and once solved a great physical puzzle. But how did the Frenchman Jean-Bernard Léon Foucault come up with this idea in the middle of the 19th century? This question takes us back to the beginnings of humanity, when people in ancient times searched for explanations in the firmament. The stars served them as a representation of the world of the gods. Until the year 600 BC, the prevailing idea was that the earth was a flat disk on which hellfire burned, and the stars were merely holes in the heavens through which one could see the fire behind it. In ancient times, the Greeks systematically observed the world and founded natural philosophy. They discovered that the earth is curved and therefore must be a sphere. One of the most influential natural philosophers of this time was Aristotle, who postulated that our planet was made up of the elements water, air, earth and fire, with earth being the center of the world. In the 2nd century AD, the mathematician Claudius Ptolemy reinforced the prevailing worldview that the sun and planets revolved around the earth. However, a mystery remained. Ptolemy could not explain the orbits of the planets. It took more than a millennium for the ancient worldview to begin to shake. In the middle of the 15th century, Johannes Gutenberg invented the printing press, which spread scientific knowledge more quickly. The discovery of America in 1492 seemed to confirm the spherical shape of the Earth. At this time, the Dr. Nicolaus Copernicus was studying Ptolemy's worldview. While studying ancient writings, he discovered that in ancient times, the Greek Charistias of Samos had the idea that the Earth orbited the Sun. Copernicus never let go of this revolutionary idea. Although he could potentially explain the planetary orbits, he was reluctant to publish his work for fear of the Church. It was only 30 years later that Copernicus took the step and published his 3 theses. The Earth rotates on its own axis. The Sun is the center of the universe, and the Earth and the other planets revolve around it. But even Copernicus' calculations could not fully explain the orbits of the planets. 50 years later, the astronomer Johannes Kepler began researching the records of planetary movements. Fascinated by Copernicus' writings, he worked on his calculations for 4 years until he finally had the decisive idea. In 1609, Johannes Kepler published his Astronomia Nova, in which he postulated that the planets move in ellipses around the Sun and move faster as they approach it. This movement of the planets is caused by a force emanating from the Sun. But Kepler was unable to explain this force. At the same time, the mathematician Galileo Galilei heard about the invention of the telescope and, using the best lenses of his time from Venice, significantly improved the magnification. This allowed him to observe the sky better than ever before and discovered the 4 moons orbiting the planet Jupiter. This was the first evidence of the Copernican worldview. However, this discovery contradicted the Church's worldview, which claimed that only the Earth could be the center of circular motion in the universe. The Church forced Galileo to renounce his convictions and, resigned, he turned away from research. But the mystery surrounding the Sun's mysterious attraction remained. In the mid-17th century, science became more important, and scholars began to once again discuss what kept the planets in their orbits. The English natural philosopher Isaac Newton studied the theories of Kepler and the laws of free fall of Galileo. It is said that a falling apple inspired him with a crucial idea. The mass of a body exerts an attraction, and the larger a body is, the more mass it binds to itself. This explains why the moon orbits the Earth and the planets revolve around the sun. Newton's laws for the movement of bodies still form the basis of mechanics today and are considered mathematical proof of the Copernican worldview. However, a mystery remains. Practical proof of the Earth's rotation is still missing. Another 150 years passed before Léon Foucault came up with an idea to prove that the Earth actually rotates on its axis. According to Newton, a body does not change its motion unless a force acts on it. A pendulum therefore maintains its direction of oscillation. But because of the Earth's rotation, we see a change that is most noticeable at the poles and decreases toward the equator. In 1851, Foucault presented his experiment to the public, providing proof of the rotation of the Earth. But with that, a new mystery emerged. Is our solar system the center of the universe, or do we revolve around something much larger? Today, we know that even our galaxy is only a tiny part of the universe. The mystery surrounding the nature of the world has shifted to new dimensions, but remains intact. Is there an end to the universe? Just 100 years ago, we only knew the Milky Way. Today we know of billions more galaxies. But is the universe really infinite, and why is it expanding? New answers are to be provided by the Planck satellite, which captures a special light, the cosmic background radiation. This radiation is the light left over from the Big Bang. As long as the light is not stopped, it continues to move and is on the move forever. When we receive this light today, it comes from every place we can see. It is radiation that comes from behind the galaxies, hence background radiation. By catching them today, we see what the universe used to be like, so astrophysicists can look into the past. This is possible because light travels at a certain speed that never changes. The speed of light is 300,000 kilometers per second, which is 7 times the revolution of the Earth. A beam of light takes 8 minutes to travel from Earth to the Sun, 4.3 years to the nearest star, and 25,000 years to the center of the Milky Way. The light from neighboring galaxies only reaches us after 2.5 million years. The background radiation, on the other hand, is older than any light that we know of. It radiates evenly at us from everywhere, and is recognized by physicists based on its wavelength and very low temperature. In addition to the visible light from the stars, there is also invisible light such as the microwave background radiation, which we can record with a microwave receiver. In principle, we can use this to take a photograph of the early universe. It all started with the Big Bang 13.7 billion years ago, when hot plasma filled space, which continued to expand. It was only after 380,000 years that the universe cooled sufficiently so that the particles of matter could combine to form atoms, and light had a free path. As the light from the Big Bang continued on its path, space expanded, and with it the wavelength of the light. This is where cosmic background radiation differs from other radiation. The Planck satellite receives cosmic rays from all directions, from which the background radiation is filtered out. A sky map of the primordial cosmos is created. On this map, temperature differences in the primordial light can be seen in the 100,000th range. These temperature differences show regions that have compacted slightly and regions that have expanded somewhat, so-called density fluctuations. The analysis is intended to show whether the universe is finite, which is possible according to the theory of relativity, although difficult to imagine. However, so far there is no evidence of this. In addition, astrophysicists hope to gain new clues about the forces that hold the clusters of galaxies together and cause the universe to expand. If the theory that dark energy and dark matter make up 95% of the universe is true, the universe could potentially expand forever as galaxies would move further and further apart. However, if the theory is incorrect, the attractive effect of the matter we know could at some point stop and even reverse the expansion, which would lead to collapse. Those are the theories, but back to the laws of nature. In our understanding, natural laws are universal, which means they apply not only here on Earth, but also in space. The law of gravity applies even on other planets, in other solar systems, and in other galaxies. However, modern physics has a surprise for us. According to string theory, our universe is just one of many. There are 10 to the power of 500 different universes, parallel worlds in which everything is a bit similar, possibly even with changed laws of physics. Our universe is governed by our laws of physics, including the law of gravity. Here on Earth there is an atmosphere, which is why, for example, a feather is slowed down while a hammer falls to the ground faster. The same experiment was conducted on the Moon during the Apollo 15 mission by astronaut Scott. On the Moon, both objects fell to the ground at the same speed because there is no atmosphere. Albert Einstein used his theory of relativity to establish that the speed of propagation of light is constant and always has the same value. This led to a revolution in our worldview, and since 1905, this amazing phenomenon has been repeatedly confirmed through experiments. One of the most important pillars of Einstein's theory of relativity states that nothing can travel faster than light. Astronomers were only recently able to confirm this law with a supernova. At exactly the same time as this star explosion, the so-called neutrinos arrived, which also obey Einstein's principle. But it is precisely these neutrinos that could potentially disprove Einstein for the first time. At CERN in Geneva, physicists are working on the world's largest particle accelerator. Neutrinos travel about 30 cm in a nanosecond, just like light. However, the exact travel times of neutrinos have never been precisely measured. The idea was always to measure times, but the requirements were to be accurate to 100 nanoseconds. Then the CERN researchers decided that a more precise measurement would be possible, and so the OPERA experiment was created, which is intended to measure the speed of propagation of neutrinos. The engineers and surveyors provided the equipment for measuring the distances and transit times, while their colleagues in Italy were supposed to collect the neutrinos from the CERN laboratory in Gran Sasso. Neutrinos penetrate everything without any resistance. Nothing stops them on their way through the rocks. First, the physicists used GPS to determine the direct distance with an accuracy of 20 centimeters. It was exactly 731 kilometers, 278 meters and 0 centimeters, and so the OPERA experiment could begin in spring 2011. The task at CERN was to produce the neutrinos in its 27-kilometer long accelerator. They were bundled precisely in an apparatus and then shot towards Italy in a straight line through the Alps to the Gran Sasso. in packages that were tens of thousands of nanoseconds wide. When the neutrinos arrived in the laboratory, the physicists stopped the synchronized clocks and read the transit times. The first major measurement campaign started in March, during which hundreds of thousands of measurements were carried out. There was no doubt that Einstein could be wrong. But the first results were completely surprising. The physicists repeatedly divided the route from Geneva to Gran Sasso by the transit times, and the result was incredible. The neutrinos were always faster than light, by 53 nanoseconds to be precise. The shock was deep and an agreed silence prevailed. A measurement error? Were the tens of thousands of nanosecond packets too large? The question of a stupid error arose, and the entire measurement technology was put to the test. Was the distance correct? Even an earthquake in the Alps that slightly changed the distance was taken into account. In response, a comparably shorter beam was sent, but the new campaign also showed similar results to the previous experiment. The researchers went public in September 2011. Wasn't Einstein right? His principle was the cornerstone of the theory of relativity. If he were questioned, everything would collapse. The most elegant physical theory of modern times would be wrong. It was found that the neutrinos from Geneva to Gran Sasso were actually faster than light. Now there are several options. Either the measurement was correct and the neutrinos are actually faster than light, which would mean a revolution, as the laws of physics would have to be rewritten. Our worldview would be put to the test again. Or an error has crept in somewhere and we are faced with a fundamental problem in elementary particle physics. These experiments are gigantic and expensive. International collaborations and large-scale experiments are crucial. What is needed now is a second experiment. In science, it is important that phenomena are reproducible. If this were the case, we would have a new puzzle in physics.